Hello folks, how's it going? Mike coming back at you with yet another video on Foundations of Math 2. In the previous video, we wrapped up our chapter on logic, logical forms, truth tables, logical connectors, quantifiers, and a whole bunch of other fun stuff. In this video, we are going to get into some common sets of numbers that we work with in mathematics and some properties related to them. So we will get started in this video with the set of natural numbers, also known as the counting numbers. This set consists of the numbers 1, 2, 3, 4, 5, 6, all the way up, so on and so forth. We represent this set by n, or this sort of fancy looking n here. Usually the way we write this by hand, if we're going to write it in such a way, would be like this. We put the two lines, the two vertical lines on the left hand there, or on the left hand side there, and then we write the n. So as a set in roster notation, this is how we write the set of natural numbers. And what we're going to spend some time looking at in this video is a natural number, little n, and factors, and all the properties of a number related to factors. So we study factors of a natural number n. Factors are the numbers that when you multiply them, it gets you that number little n. And every natural number can be written as the product of two or more other and smaller natural numbers. Now, once we get a little bit later on in this video and we learn some other terms and their definitions, we're going to tweak this statement just a little bit. But for now, every number can be written as the product of two or more natural numbers. For example, we can take the number 30 and write it in the following ways. We can write it as 1 times 30, 2 times 15, 3 times 10, or 5 times 6. These are just some of the ways that we can write 30. We see that in each of these four cases, both numbers involved there are natural numbers. So in this case, we said there are multiple ways to write 30 as a product of two natural numbers. That is to say, there are factors of 30 besides just 1 and the number 30 itself. And when a natural number has factors other than 1 and itself, we say that that natural number n is composite. Some of us may recall this word from maybe some time back, maybe not that long back. But when a number has factors other than 1 and itself, we say that that number is composite. We say that a natural number n is divisible by another natural number k if dividing n by k results in a remainder of 0. That is to say, if you divide n by k and you get another natural number. This is really the way that you want to look at divisible for now. For example, we say that 30 divided by 6 is equal to 5. Or we see that that is the case. You can plug that into your calculator. So we took 30, we divided it by 6, we got it by 5, which is a natural number or a counting number. So we say that 30 is divisible by 6. And we can do the same kind of thing, and we can say the same kind of thing with 1, 2, 3, 5, 10, 15, and 30. In every one of these 7 cases here, you can take 30, divide it by any one of these numbers here, and the number that you'll get is a natural number. It is a counting number. Therefore, we can say that 30 is divisible by any of these 7 numbers. But in some cases, we can only write a natural number as a product of 1 and itself. Case in point, if we take the number 23, the only way that we can write 23 as a product of 2 natural numbers is 1 and itself. When this is the case, when we can only write a natural number, and we specify that the natural number has to be greater than 1. So when we can only write a natural number as a product of 1 and itself, we say that n is prime. So prime numbers, the only factors are 1 and itself. Composite numbers, it has factors other than 1 and itself. So earlier we said we can write any natural number as the product of 2 or more natural numbers. Now that we know the definition of a prime number, we're going to change that statement just a little bit. And here's what we're going to change it to. We can write any natural number as a prime number or as a product of prime numbers. And this is actually a really basic yet important theorem in the world of mathematics. It's called the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. And not that that's something you have to know off the top of your head, but just I wanted to point it out to you there that this is a very basic yet important theorem in the world of numbers and mathematics. Just wanted to give you the first 10 prime numbers that occur in the set of natural numbers. Those are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And we're going to be using these primes in the next little batch of problems that we can see from this section. So if our given number n is not prime, if we know that there are other factors of the number besides 1 and itself, how do we write that number as a product of primes? And when we write it as a product of primes, what we're doing is we're writing the number in its prime factorization. I apologize. And there's a couple different ways we can do that, but these methods are at its core the same thing. The main difference is just how we are representing it. So method number 1, the tree method. What you're going to do is you're going to start with your given number and start with that first prime that we saw in our list of 10 primes here. Start with 2 and see, can I take my number and divide it by 2 and be left with another natural number? If I can't, then that number that we're given is not divisible by 2, and we try the next one up. So I look at 75. If I try to divide it by 2, I am not going to get a natural number as a result. So I'm going to go to my next prime up. I'm going to try 3 here. 75 divided by 3 does give me a natural number. It gives me 25. So what I'm going to do is I'm going to create some branches off the top here. I divided that 3 out, and that got me 25 left over. So in the end, we want to get this down to something where every number is a prime number all on its own. So we know that 3 is a prime number. 25 is not a prime number. So we have to see what prime, or just what number can we divide 25 by and get some other natural number. So we're going to do the same thing as we did with 75 with 25 here now. If I try to divide 25 by 2, will I get a natural number left over? No. So I have to go to my next prime up. If I try to divide 25 by 3, will I get a natural number left over? No, I will not. So I need to go to my next prime up. 25 divided by 5. Will that get me a natural number left over? And it turns out I will. And when I do 25 divided by 5, I get 5. So 25 divided by 5 gives me 5, or 5 times 5 gives me 25. Note that we carried that 3 down just to keep everything in the same row. And now we have 5 and 5, which we know are both prime numbers. 3 is a prime, so we're done. We've reduced this thing down to something such that every number in this bottom row here is a prime number. So now we can write the number 75 in its prime factorization. And it's just going to be the product of every number that's down here. 3 times 5 times 5. And there we go. That is the prime factorization for the number 75. So another one here, a little bit larger of a number, 180. Let's try to do the same kind of thing here, and let's try to find the prime factorization for 180. I'm going to start with my smallest prime. I'm going to divide 180 by that number. If I get a natural number left over, then yay. If I don't, then I move up to the next prime number. So 180 divided by 2 is equal to 90, and we then write this as 2 times 90. I have 90 here. 2 is a prime. Can I divide 90 by 2? Yes, I can. I get 45 left over. Okay. Again, note that I just carried that 2 down, just so we can have all the prime numbers at the very end. 45. Can I divide 45 by 2 and get a natural number left over? No. Can I divide 45 by 3 and get a natural number left over? Yes, I can. When I do that, I get 15. Carrying these prime numbers down. 2 and 2 and 3 are prime numbers. So the 15, can I divide 15 by 2 and get a whole number or a natural number? No. Try 3. Can I divide 15 by 3 and get a natural number? Yes, I can. And that gives me 5. We know from our previous problem, as well as from our list of some primes, that 5 is a prime number, so we are all done here. We have found the prime factorization of the number 180, and we can write it in its prime factorization. 2 times 2 times 3 times 3 times 5. Now, just as a quick note, You see me using the X's here to stand for the multiplication symbols. It is also very common that you'll just see me use dots here. Dots also mean the same thing when we're at this basic level of mathematical operations here. The dot also means times. So this is the tree method that we can use to figure out what is the prime factorization of a given natural number n. Method 2 is the division method. And again, at its core, same thing as what we did with the tree method, but we're just not drawing out pictures. We're not taking up a whole bunch of space. So here's how this method works. You're going to divide the given number by the smallest prime until you can no longer do so. Then you're going to move to the next prime up, which is 3, and you're going to divide what's left over until you can no longer do so. And you're going to repeat this process until the number that you're finally left with after dividing all that you can is a prime number. Then to write the prime factorization, you're going to write the products of all the times that you divided by 2 and 3 and whatever other primes, and then that last number that you are left over with. So we'll see that in a sample problem here. So we're going to find the prime factorization of 360. So I'm going to take this number, I'm going to divide it by 2 as much as I can. So 360 divided by 2 is 180. All right? I can divide 180 by 2, that gives me 90. I can divide 90 by 2, and that gives me 45. Now, if I tried to divide 45 by 2, I would not get another natural number. So I can't divide by 2 anymore. This is all done. I now have to move up to my next prime, which is 3. I can divide 45 by 3, and that gets me 15. I can divide 15 by 3, and that gets me 5. And I look at this number here that I have left over, and I realize that this is a prime number. This was on my list of the first 10 primes. So I know that I have to stop here. Now, I have to write the prime factorization of my number, 360. And what numbers go into the prime factorization? Well, it's all these numbers here that followed your division sign there. All those guys, as well as the last number here that you had left over, as well as that 5. So it's going to be 2 times 2 times 2 times 3 times 3 times 5. And that is the prime factorization for the number 360. So try this next one on your own. Try to find the prime factorization of the number 420. Go through that same process of start with 420, divide by 2 as much as you can. Once you can't divide by 2 anymore, move it up 1 prime, divide by 3 as much as you can. Do that, then move it up 1 more, divide by 5 as much as you can, and then write out your prime factorization. So press pause here, try to solve the problem on your own. Once you think you have it, press play, and we will see if you were correct. All right, so let's see if you came up with the correct answer. Just to get us started here, I can divide 420 by 2, and that gives me 210. I can divide 210 by 2, and that gives me 105. If I try to divide by 2 once again, I cannot do it. I don't get a natural number, so I have to move up to my next prime of 3. I can divide 105 by 3. That gets me 35. If I try to divide by 3 again, I don't get a natural number, so I now have to move up one more prime, and I have to divide by 5. And if I do 35 divided by 5, I do get 7. And from our list of primes, 7 is a prime number, which means this is where I am going to stop. And I can now write my number in its prime factorization. 420 equals 2 times 2 times 3 times 5 times 7. Now, similar to what we have written here, I could combine those 2's that I had, and I can put an exponent on that prime of 2. I had 2 times 2, which is the same as 2 squared. So I could have taken this thing here and written that as 2 squared times 3 times 5 times 7. And when you take your prime factorization and write it as the product of these prime numbers raised to powers, what we're doing is we're writing the number in its canonical form. And we're going to see how writing a number in its canonical form can be very, very handy for us. Given two natural numbers, a and b, the greatest common factor, or the greatest common divisor of a and b, which we denote as GCD of a comma b, this is the largest number that is a factor of a and b individually, yet at the same time. So how do we find this GCD? How do we find this greatest common divisor? So there's a process that we go through here. First, we're going to write the canonical form of each number, a and b, separately. So that means going through this method of finding the prime factorization, writing things as primes raised to powers. Then, for each prime that occurs in the canonical form of both a and b, we're going to take that prime and we're going to raise it to the smaller of the two powers that appears. So what I mean here is, suppose in a you have 3 squared, and suppose in b you have 3 cubed. We're going to have that prime of 3, but for the GCD, we're going to raise it to the power of 2, the smaller of those two exponents, or those two powers. 3, we're going to take the product of all the numbers that we found in step 2, and whatever that product is, that is our GCD. So this seems like a confusing process just written out as such. Let's see how we do it with a sample problem. So let's find the GCD of 75 and 180. First thing we have to do is we have to write each of these numbers individually in its canonical form. To do that, we need each of these numbers in their prime factorization. Well, we found the prime factorizations of each of these two numbers, so we'll just copy those over from previous slides, and then we'll write each of those in its canonical form. 180 was 2 times 2 times 3 times 3 times 5. That's the same thing as 2 squared times 3 squared times 5, or 5 raised to the power 1. And then we have 75, which is 3 times 5 times 5. which is 3 to the power 1 times 5 to the power 2, or 5 squared. Next up, we're going to determine each prime in the GCD and its power. So once again, to figure out the primes in the GCD and the power on that prime, we need primes that show up in both numbers. So in 180, the primes 2, 3, and 5 show up. In 75, only the primes 3 and 5 show up. So the two primes that occur in both numbers at the same time are 3 and 5. Now we have the primes. What are the powers on these primes going to be? I'm going to change colors here. So looking at the 3, we have 3 to the power 1 and 3 to the power 2. We're taking the smaller of those two powers, and that power, that smallest power, is going on the prime in our GCD. So the smaller of 1 and 2 is 1. So we put the 1 there. The other prime that they have in common is 5. Here I have a 5 to the 1. Here I have a 5 to the 2. Again, I'm going to take the smaller of those two powers, the 1, and that's going to be the power on the prime 5 in my GCD. Last step is to multiply these numbers right here, and whatever that is our GCD. So I have 3 to the 1, or 3, times 5 to the 1, or 5, and that gets me 15. So 15 is the GCD of the numbers 75 and 180. Try this guy on your own. Try to find the GCD of 108 and 224. Once more, take each number, write it in its prime factorization, and then change that into its canonical form. Then you're looking for the primes that occur in both numbers. You take those primes. The power on those primes is the smaller of the two powers that occur in the number separately. Then you have primes raised to powers. Take the product of those numbers you find in step 2, and that is your GCD. So press pause now. Try to figure out what the GCD is. Once you think you have it, press play, and we'll see if you are correct. All right, let's see if your answer was correct. So the canonical forms for these two numbers, 108, 2 times 2 times 3 times 3 times 3. That is 2 squared times 3 cubed. And then 224 is 2 times 2 times 2 times 2 times 2 times 7. And that is 2 to the power of 5 times 7 to the power of 1. Now we're looking for what numbers or what primes occur in both of these guys at the same time. Well, there's only one prime that's in common here, and that is the prime 2. So it's going to be 2 raised to some power. What is that power? Well, here we have 2 squared. Here we have 2 to the 5th. So we're going to take the smaller of those two powers, which is 2. So in this case, this is all we have. We simply find what this is equal to. 2 squared is 4, and that is our GCD. So these are just a couple sample problems here showing us how we can find the GCD of any two numbers. We could do the same kind of thing with even larger numbers, but we're not going to deal with numbers too large. 3 digits is the maximum that we will go. So related to the greatest common divisor, or the GCD, is something called the LCM, or least common multiple. Given two numbers A and B, the least common multiple of A and B, which we denote by the LCM, is the smallest natural number K, such that A is a factor of K and B is a factor of K. And once you've found the GCD, finding the least common multiple is very, very easy. There's just a couple small calculations that you have to do. And how you find it is based on the following fact. For any two natural numbers, A and B, the product of A and B is equal to the product of their GCD and their LCM. So you'll be given what A and B are, you'll have found their GCD, you then just have to find their LCM. You just take the product of your two integers and divide that product by the GCD. So working with the sample problem that you just did on your own, we want to find the least common multiple of 108 and 224. Well, you found that the GCD was 4, so we just do a quick calculation. 108 times 24, or times 224, my apologies, equals 4 times the least common multiple of these two guys. So the least common multiple of 108 and 224 is going to equal 6,048. And you could have put 108 here and 224 here, or vice versa, does not matter. So that's how we find the least common multiple, and this concludes our video on the natural numbers, what they are, as well as all the studying of factors of natural numbers, prime numbers, composite numbers, prime factorizations, canonical forms, GCD, and LCM. In the next video, we are going to take a look at the set of whole numbers and the set of integers. If you have any questions or comments, please be sure to reach out to me. Rocks through the window, texts, signs up on blimps over sporting events, anything at all. Otherwise, until the next video, take it easy, folks.